Okay. Hello and welcome to our webinar for the Equotip, where we're going to discuss how to achieve accurate hardness testing on custom materials. I am Tom Ott. I am the head of technical support for Proceq USA, and I'm here with Darius Barnett. He is the product manager for the Equotip product line. So, as we begin, we'd like to discuss why do we measure hardness? Right? Hardness is measured because it gives a close correlation to other material properties, such as strength, brittleness, what kind of surface treatment it has, and the toughness of the material. Why do we measure hardness instead of measuring those things directly? It's because hardness is a lot easier to measure than something like tensile strength, where you have to cut a specimen out of the material. Hardness can often be tested on the material itself without ruining the material or test specimen and making it unusable for its intended purpose. So before we start talking conversions and correlations, we need to understand how the hardness test methods are working themselves. Oftentimes, we're talking about portable instruments today, but we're always compared with stationary test instruments like Vickers, Brunel, and Rockwell. So those are the three biggest. There's other test methods out there, but those are the most common. With Vickers, Brunel, and Rockwell, we're applying a test force, and we're measuring some characteristic of the resulting indentation in the test specimen, whether it be the depth of indentation, or in the case of Vickers and Brunel, we're measuring the area of indentation. And because those are the native tests, those tests are material independent. A Brunel hardness of steel is going to be a Brunel hardness of equivalent titanium or stainless steel. There's no conversion within a single hardness scale. However, when we get to the portable instruments, we're measuring different parameters and that we need to account for the materials whenever we do those correlations because the material is responding to those different indentations in different manners. And it's not a linear or direct relationship. So in the case of rebound, with the Lieb method, we're measuring the rebound ratio of rebound velocity to the impact velocity. In the case of UCI, we're measuring a frequency shift as we're indenting into the surface. And with Equotip Portable Rockwell, we are actually measuring the depth of penetration like you do in the Rockwell test. However, we're using different forces and indenters and dwell times, so we get a slightly different but still material independent measurement. So whenever we get through Lieb and UCI, if we need to report our values and tests in a different scale, we need to put it through a conversion. So let's talk more about the different tests, focusing on Lieb and UCI because they are material dependent. In the portable hardness test Lieb, we have an impact device, which is a mechanical device, and we have an impact body. So the user loads the impact body against a spring that's calibrated to propel the body at a precise velocity. The user launches the body against the surface, it bounces back, and as the body is traveling through the device, it travels through an inductive coil to generate a voltage signal. That voltage signal is directly proportional to the speed that the body's traveling. So you can see in the formula to the right, we get a ratio of the rebound velocity to the impact velocity, multiply it by 1,000, and that results in the Lieb value. So it's important to note that whenever we're impacting, even though these impact bodies are small things, they are generating a pretty high energy impact that generates a shock wave that travels through the specimen under test. And that shock wave can interfere with the test result, especially if you don't have enough mass or you don't have enough thickness. If you don't have enough mass or thickness, now some of that velocity lost or energy lost during the impact, uh, it goes towards making the test specimen move or vibrate, which leads to an incorrect measurement. So that needs to be taken into account whenever you're deciding whether to do a Lieb test or some other test methods. And also in the case of all hardness tests, we need to also manage and make sure that we have the correct surface roughness prior to the test. Because surface roughness, hardness being a surface-based test, surface roughness is an important factor. So let's move on to UCI. So what does UCI stand for? UCI stands for ultrasonic contact impedance. So if you look at the graphic on the left, we have a diamond that's vibrating at a resonant ultrasonic frequency before the indentation. So the Equotip is measuring that frequency and monitoring that frequency as we make our indentation into the test material. So you, the user, press the probe into the surface, and as that diamond indenter makes its way penetrating the surface, the frequency of vibration is shifted because of the contact with the diamond and the specimen material. So as we have a soft material, we get deep indentation that produces a very large frequency shift. Medium indentation, not so much, and a harder material has slight indentation and a much lower effect on the frequency. So that measured frequency shift is converted to hardness, right? And the frequency changes due to the impedance, the contact impedance between the diamond indenter and the specimen under test. So important to remember also for UCI, there's still a minimum mass and minimum thickness required to prevent vibrations. Although in this case, the vibrations are induced by the probe tip itself and not by anything like an impact. So the probe can actually drive vibrations. And then again, surface-based test, we need to watch out and make sure that we have the correct minimum surface finish to get an accurate result. So when we talk about UCI and contact impedance, that contact impedance and that frequency shift is strongly influenced by the elastic modulus of the specimen that we're testing. As all manufacturers provide their instruments with a default conversion curve to go from frequency to hardness. Those curves are all built off of a low alloyed or unalloyed carbon steel that has an elastic modulus of 210 gigapascals. And this default calibration is generally valid within 10 gigapascals of that calibrated value. So now, as you go to start testing a different material, you need to take that into account. The other thing that's important to note is different curves for the frequency shift are developed for the different test loads. That you can see there, the blue line is for one test load and the red line is for another. So again, we need to make sure that we're not testing something that's too thin or too light, or else that vibration is not going to be properly shifted and we're going to get inaccurate or false readings. Equotip portable Rockwell is based on the traditional Rockwell indentation method. It follows the Rockwell test cycle, but again, it differs in that we're using a different test forces and different indenter shape. But because we're following that test cycle, we do have a direct indentation method and essentially material independence. So what is that Rockwell test cycle? We bring the indenter into contact with the surface, and as we press on the probe, now we cycle through a minor load of 10 newtons. At that point, as soon as we hit that minor load, we measure the depth of indentation. That gives us the D1 in the graphic below. We then proceed on to add an additional load of 40 newtons to provide a total of 50 newtons load, and we hold it for a dwell time. The Equotip is very nice in that it gives the user a graph that they can watch and they can get confidence that they're getting an accurate measurement. And whenever the dwell time is reached based off of the indentation depth and material creep, the unit Equotip tells you to release. And as you release that force, it cycles back through that minor load and measures the depth again. That gives us depth measurement 2. And depth measurement 2 and depth measurement 1 provide a difference. And that depth difference is then calculated into the hardness. It gives us a direct measurement of the hardness. So in summary, right? We need to be careful with different things whenever we talk about the different test methods. With lead, we start off, we need to have a minimum mass and minimum wall thickness, and of course, the correct surface roughness. And we need to make sure that we use the correct conversion for the specimen that we're testing. Lead has 9 material groups, and as you go to the boundaries of those material groups, Darius will speak of that a little bit later, then you need to consider doing a custom conversion. UCI, again, minimum mass, minimum wall thickness. You can test thinner things with UCI. That's one of its great advantages. Uh, but you still have to be aware of those minimums. You have to have the correct surface roughness. And UCI is a lot more sensitive to the alloy change. So anytime you get away from that 210 gigapascal modulus of elasticity, you need to concern yourself and start considering using a custom correction. And then again, Equotip portable Rockwell. All we really need to concern ourselves with is minimum thickness of 10 times the indentation depth. We need to make sure that we can hold the probe flat without vibrations on the test specimen. And it generally doesn't need a correction or a custom correlation. The only time you need to do that really is whenever the pre-programmed hardness scales that we have are not one of the hardness scales that you need to report your results in. So again, when you correct your measurements, you need to be free from any mistakes in mass, wall thickness, surface roughness, and specimen calibrations. So with that introduction, we have a question for everybody. What materials and specimens are challenging for you? So please feel free to place your answers in the window that popped up, and we'll give you a few minutes to do so. All right, excellent. Looks like we're getting some good responses here. Can't wait to read them. Okay, well, in the interest of moving along and saving time, I think I'll pass over to Darius to continue the presentation. And if you didn't get the chance to type your question in the poll, we can always address your question at the end. Now, over to you, Darius.
Thank you, Tom. Thanks for a nice introduction. I think this is a very important thing to highlight the fundamental things because first we want to learn the fundamental things and make one step farther. So in today's presentation, we started talking about Leap, UCI, and Rockwell just to highlight the Leap is actually E-modulus, right? Thank you for letting me know. It's evilness of technology, which simply kicked me out. Let's try to recap once more. When Um, Screen one. Sure. All right. Please let me know if you see my screen. I had an issue with the PC.
Yes, we can see your screen, Darius.
All right. Thank you very much, Tom. So let's get back on track. Out of those three methods that we discussed earlier, lib and UCI are E-modulus dependent. Especially UCI is very strongly elastic modulus dependent. So for lib, a user has already 9 different predefined groups, which are steel and cast steel, cast iron, cast aluminum, or bronze, just to name few. You will see them on the screen right now. Those were developed 40 years ago by us at Proceq, and currently they are actually implemented pretty much in all of devices on the market, not only ours. Nevertheless, they allow you to tune up when you convert a leap unit into another unit. So you can choose out of those materials and carry on with your measurements and have correct readings. The UCI is a little bit more challenging, as Tom already highlighted. It is strongly Young modulus dependent. So there, it is really important to apply those corrections. And so once more, all of the probes on the market, all of the hardness testers on the market, they are calibrated to default cast steel and cast steel with elastic modulus of 210. To close that, the Rockwell is material independent. So what we also have, we have a little bit advanced solution. So for example, there are groups of materials which are also being tested, which are not included in those groups. And for example, one of our devices, which is Equotip 550, does have that feature, especially alloys for power industry, high alloy steels, which you can see, you can find it over there. And then on the UCI side, you also can benefit from additional conversions like aluminum P91, 304L, for example, just to name a few. And you can apply your own corrections to pretty much any material on the market. So let's stop a little bit for a second with the leap. Why there is a challenge. So although the users, they can choose out of the materials they are testing, it is very important to highlight that the materials defined by the standards, whether this is NCS, TM, and so on, they have their tolerances. So here on this chart, you see all of those 9 material groups which are available in our devices, in competitors' devices, but there, those blue fields, they represent the ranges of the air modulus defined by the standards. So the very first conclusion you might have from there, so the average value, which you see represented by the red dot, has already a range. So that's one very important thing to remember. The second one is quite often, although not always, the material we're purchasing, you're working with is a little bit away from those default materials. So these are non-standard materials and you cannot have sometimes ideal solution for that. So this is a challenge when you want to be as accurate as possible, and the solution is simply you need to adjust the measurement output to have a correction, and those are done through conversion curves. So over to UCI right now. Let's have a look a little bit deeper in what Tom already has highlighted with the principle behind the ultrasonic content impedance, which is namely frequency shift. So here what you see is a resonator, which resonates in the air with default frequency. For the purpose of our today's webinar, let's stick to 85 kilohertz, although different manufacturers, they have slightly different technologies. So at 85 kilohertz, the resonator vibrates, and obviously, as already mentioned, if you make an indentation, let it be still with the value of 150 Vickers. And this still has default Young modulus of 210. So exactly the same how devices are calibrated. The frequency changes down to 80 kilohertz, so you have a 5 kilohertz difference. We can simplify that and say that there is a damping effect between from the contact of the diamond with the material. So this damping effect is being there. Now let us consider another material with different elastic modulus, but the same hardness. So here you see a custom material of exact same hardness as the one before, 150 Vickers. The material has elastic modulus of 105. That means a half of where the device was calibrated. And here an interesting thing happens because the resonator resonates faster at 83 kilohertz. So this damping effect is not as pronounced as it was earlier. As a result, let's say the device thinks that because of those 2 kilohertz, it's going to provide you the output of 500 Vickers, which is simply incorrect because we know it's 150 Vickers. Similar conclusion you can do when you, for example, measure aluminum with default steel conversion curve. You might end up with values even up to 5 or 600 Vickers, which some people know who are in the topic that it does not exist. So how comes? It is simply because of the resonation frequency. And this is another reason when there is a deviation in the Young's modulus to apply the appropriate correction. So what do standards say about that? And all the standards globally, whether this is ASTM, whether this is German standard, or whether this is DIN, they all say you have to apply a correction if you measure something different. So it's not only our invention of the manufacturer's invention, it's simply standards do require applying corrections if you measure anything different than that. Now, going further to this, and let's iterate once more. Default conversion is 210. So here you see a short overview of some metallic materials and their differences in Young's modulus. So as we already mentioned, 210 would be the default calibration. Give or take 10 gigapascal. So anything within this range can be, technically speaking, tested successfully according to standards, and it's absolutely correct. One thing is certain, that for example, if we take P91, and depending on the manufacturer, its value can vary between 217, 219, so you're really very close to the edge. I need to highlight that at this stage, although the measurement standard compliant, you're already having a small bias because of that fact of different Young's modulus. So if you go further to titanium alloys or even aluminum alloys, which I just mentioned, you're completely far away from the default calibration and you need to apply it. And there are three ways how you can do that. So when do we want to convert those values? When do we want to have those conversion curves? So conversion curves are used all for custom materials in case of portable devices, but also conversion curves are used to convert one scale to another, for example, also for the benchtop devices. And they are standards, ASTM and ISO standards, which allow that, which show comparative tables. We're going to get to this point in a second. And in other words, we have two use cases for the conversion curves. Either we generate one value to be expressed in another, for example, because let's say a subcontractor or a client wants to have different value, different unit to adjust to their processes, or because they have different processes. And the second one is when we use material-dependent methods like LEAP and UCI. So let us very shortly have a look how those conversion curves are made. Here, on the left-hand side, you see actually a screenshot from ASTM E140, and you see a set of points. So here on the bottom, you see a LEAP scale and HRC scale. In very simple terms, each of those points represents an average of a specimen which has been tested with two different methods. In this case, it's a LEAP and HRC, and so on. Each of those points represents a specimen of different hardness, and if you have them generated and measured, you can simply create a mathematical formula that expresses the relationship between them. And as an output, because of that curve, you will receive a conversion table, which as you see right now is ASTM E140 for steel and cast steel. In summary, everything starts from the measurements, from the empirical measurements, and compares through the mathematical equations to a table. So here on this slide, you see it a little bit better that in fact, each of those points, which we've seen earlier, is an average of several measurements. And this is something I want to reiterate once more. One hardness measurement is better than zero, but it's not much better. Typically, 5 measurements would be something that a user should take into account. We're going to get there in a second. Second important message I want to mention is this: there's no mathematical formula like in case of physics when we discuss, let's say, speed and acceleration. This is purely empiric and comparative method to convert one value to one unit with a value A to a unit B with a value B. So all of those things are typically standardized. And those conversion curves have obviously some limitations. And when we want to stay accurate, we need to be aware of those limitations, what can be done and what can't be done. If we look exactly at the process which I briefly described earlier, we always start with correctly prepared samples. And this is very important, what Tom already highlighted. If we select a method like LEAP or UCI, we always need to remember that there are specific limitations starting from the mass and wall thickness for both. So if we choose the samples which have incorrect geometry, which may impact the result output, then we're actually not really applying the right thing. It's not really a correction. To some extent, perhaps it is, but it's a wrong one. So in parallel, we start with measurements from both devices, and we need to correlate it typically to a benchtop device. And then, literally speaking, we need to tell a device, whether this is our device or any other device on the market, hey, this point of this value is actually representing another value. So with mistakes, I want to highlight once more, and later on I will show you some examples where things went really wrong with conversions. These are customer conversions from our customers that we helped with. And thank you very much at this stage to those customers who enabled us and allowed us to showcase that. It is very important that the mass and wall thickness are really not causing a measurement distortion. And one important thing I want to highlight at that stage is the surface roughness. Once more, the surface roughness is extremely important because we use much lower forces compared to benchtop devices. So while for benchtop devices, when you apply a very high load, it plays a secondary role. For the hardness testing devices, up to 60% of mistakes from different users is being done through the wrong surface preparation. So a second thing is, how many measurements should I take? Let's have a look at that from different perspectives, and let's see what standards actually say. Some users, and this is a common practice, they would take 3 measurements. So those measurements here are presented with those teal lines, and the red is average. So if everything works fine and you carry on doing further measurements, the average does not change. But it is generally a good practice to have a higher statistics, because it might happen that additional measurement points are going to change your average. So the conversion you would be applying to your material, and perhaps, let's say, to a production line measuring different materials, will be simply wrong. So one thing is important is to pay attention to the data span. So standards generally require 5 measurements on the benchtop. Some customers work outside of the standard, and for them 3 measurements is just fine. But it is important to highlight, at least from my point of view, that standards are demanding that. So when it comes to the portable devices, 5 obviously is minimum, and is also what standards require. But because those measurements with UCI or LEAP are extremely fast and extremely easy, it does not harm much to do additional 5 to have really a proper and representative statistics. Then when we compute the average values, one thing what I want to highlight is this is a desired, a close, let's say an average, and the single data point is very close to its average, so the span is very low. And what is not desired is when you have really uh, a big data span, as you see here, which might indicate that, for example, your test piece you have selected is simply inhomogeneous. When it comes to portable methods, besides the inhomogeneity, you can have also one simple thing. So portable methods, they have a user between the final output and the specimen. So user can also make mistakes. Typically with benchtop devices, we tend to believe those mistakes are not there. But in case of here, for example, a rope probe application, wrong surface preparation, and again, wrong thickness or wall thickness or weight, they can cause that effect. So it is also important to highlight that inhomogeneity might be one thing, but not necessarily that can be also other mistakes, and those mistakes we should avoid, especially at this stage. So, what would be the correct and the best practice methodology to apply the conversion curves, right? So first, if we use LEAP and UCI, once more, we need to be sure that the test specimens we are having are appropriate for the test method. And the second one would be correct, let's call it low surface roughness, and this applies to all portable methods, also portable Rockwell. A third one is what we have not mentioned so far, but we need to clean our samples. It's also one of the most common mistakes being done. Some people believe that if they indent something with a diamond, then it goes through, but in fact, they block the interface with the diamond of the UCI contract impedance. So it is also important to get rid of debris, get rid of grease, and just to clean up the surface. Lastly, material homogeneity. If our material is inhomogeneous, then the outcome might be simply different. So we need to be sure that if you're selecting a material, it's really a homogeneous one. Sufficient number of measurements. This is something what we already discussed. 5 is requested. 10 is the maximum. Afterwards, there should be no further improvement. And the proper indentation spacing. So we should not, we should never hit one same spot several times because the surface gets actually hardened, so you're getting falsified results. Now, what happens if we want to apply a correction within a specific organization which is regularly audited? Because there are no standards actually behind that. It is important to understand specific requirements or very often looked after requirements. So let's say, for example, the test pieces, they should typically fulfill the requirements of the method. If you choose LEAP, ideal case, it would be that we generate a material which is of the size of the test block at least, so we prevent those vibrations. A second thing for UCI, typically 16 millimeters and 80 millimeters in diameter, those are standard compliant test blocks. And a very good practice would be to send it to external laboratory, which is accredited, although the accreditation is not always demanded, but it definitely helps when it comes to the traceability. What is also important, but also not often required, however, it might help if your portable equipment has a valid and accredited calibration certificate, which will be very often subjected to questioning by the auditors. So if you fulfill those requirements and if you eliminate those basic results, you should not have issues throughout the auditing process because those are the critical parameters that auditors might be searching for. Now, there are typically three methods how you can apply a correction. So very first one is one-point correction. And here, at least in our device, we offer two subvariants of this one. Then there is a two-point method and a polynomial method. So there are three distinguished possibilities you can apply, and it really depends on the user's capability. but also it depends on the measurement range and what you really want to achieve. So let us dive into details shortly into each of those to learn about their limitations and advantages. So here on this slide, you see actually an interface from our device, but I'm using this because it shows clearly what is really happening. So the teal curve, which you see here, is the existing curve for a material. And those two orange points are simply methods, the same materials measured externally with the benchtop device. So in this table, you're simply comparing those values. Let's take a very first one here, which is 308 Vickers. Typically, without the correction of this specific material, it would be around 32 HRC. But since we have done this research and we have done this study, we know that this is actually 35 HRC. And here, consequently, so at 930 Vickers, the value should be just around 60, 67 HRC. Nevertheless, the results has showed us that this is in fact 69. So by remeasuring this, instead of using a default conversion because this material is slightly different, we're obtaining a new one. So the new conversion, when it's generated, can be used to measure that specific material. And this is a two-point conversion curve. It's much more accurate than the one-point shift. And the reason behind this, should you conduct only the one-point shift, you would learn that there is a specific range where the one-point shift can be applied. So in other words, the number of those measurements, they increases the range of the curve and the validity. And here it is important to understand that if you apply a one-point shift at specific range, you should not expect that this will hold across the entire measurement range, and you should be aware that you might be having inaccurate results. The last one is the polynomial curve, and this is something I will discuss in few steps on the next slides. And the polynomial curve, it's nothing else as the conversion standards are doing. In this example, which is a custom brass material with approximately 100 gigapascal Young's modulus and measured with UCI and measured with Vic stationary Vickers, you will have a set of, in this case, 5 specimens. So what you see here, for example, is that this value differs significantly from this one. And based on our beginning of our webinar, this is to be expected because the Young's model is completely different. Similar results you would have measuring aluminum, titanium, and any other non-standard material which falls outside of this default calibration. But having those materials measured, what you typically tend to do is you tend to display them in any Excel spreadsheet or any other calculation spreadsheet which can compare the UCI values with benchtop Vickers values. In the next step, what you would do is you would use a mathematical formula, and we use the polynomial curve to describe the mathematical relationship between them. So we're actually getting here an equation, and this is fairly easy. Excel is fairly easy to be used, for example, and it's very cheap, often free of charge software for this simple task. And as a result, if you use this curve, you will have your conversion table, which you can use later on to manually recalculate that if you like. So some devices on the market, including all of the devices from us, they allow you to store that and use it later on. And let's see how it works on this device. So this is an Equotip 550. The device goes through a simple wizard, so it guides you through the entire process, how to implement them. And in this example, we're using exactly same conversion curve for brass. So brass cannot be easily measured with UCI because of this specific material. So what we're selecting here is a polynomial curve. And those curve parameters, which we received from, in this case, from Excel, we just simply want to transfer them into the device. So here, simply one needs to type those values in, and I will just speed up the process a little bit. And then at the end, you're generating a curve. One important thing I want to highlight is that you also need to provide a range. So here I'm applying the range where this curve should be applied. So in this case, I'm providing 200 Vickers and I'm providing 600 Vickers UCI as the range within which I want this conversion to be used for my material. And that's actually it. Now, if we go to some examples of other polynomial curves, I'd like to show you some bad examples in a nutshell and what to avoid. So here, for example, you see exactly same set of samples, but measured with HRB, so it's Rockwell B scale. And here what you see is so-called overfit. Uh, each of the polynomial curves, they provide you R value, and the meaning behind R value is the higher the value, the R value, and the maximum value can be 1, the better the correlation, the better the curve describes the data we have collected. So, but here something went wrong, and please pay attention to the way how its curve simply works. From here till here, everything works fine, but then there is something different. Our HVUCI hardness increases, but at the same time, our HRP value decreases, which makes little sense because if something gets harder in one scale, should also get harder in another scale. In this case, a user conducted some sort of overfit and he defined the wrong range. So it is generally a good practice to stay within the known range when it comes to conversion curves. And the solution for this curve, so this curve should be stopped in here. Here you see a perfect R factor. It's a very excellent one and very okay range. And here you see even slight extrapolation and interpolation because of the known curve behavior. One, however, needs to be careful with extrapolation, interpolation because it leads to some strange results, or it may. This is a perfect example how conversion curves should not look like if we want to have a high accuracy and precision. So in very shortly, this is a custom cast material with 140 gigapascal Young's modulus. So once again, this material this correction should be applied to this material. And here the customer struggled a little bit. And after investigating, first of all, the test pieces were greatly inhomogeneous. So that's why you see a data spread. Then you also could see a wrong specimen preparation. The surface was practically not really prepared. So we're talking about really, really rough surface. And if, as we mentioned, if you apply much lower forces, this comb structure, the surface, plays much higher role if you use hand tools, like in this case, portable devices. And here the customer tended to use two various polynomial curves. This one, for example, there is an overfit, and because of the data spread, the curve starts going down. So we have exactly the same problem as earlier, that the curve is simply overfitted. And in this case, the message is, although the R parameter is actually lower, it describes the whole relationship much better. Nevertheless, this should be taken as an example of high imperfection when it comes to conversion curve generation, because if you see on this scale, these values, they start varying greatly, and one should be careful with that. One more example I wanted to highlight is that some customers or some users, for example, want to generate completely a new curve. So in this case, you have leap G to HRC, which in standards does not exist. And in this case, you see a perfect combination of leap and Rockwell method. So the customer actually prefers leap method over the Rockwell method to conduct measurements because they find it much more useful and they can do much more tests with the portable method compared to the stationary one. So the customer conducted this research to simply shift the curve and achieve exact same results as with the benchtop device, but with Rockwell. And last thing, This was the last example I wanted to highlight, and in a second I would like to open Q&A session. I hope you have some questions. If you have any questions related to accurate measurements, custom materials, and conversions, we would like to guide you to our online document where you will find plenty of information about each of those curves, ranges, and how to apply them. And if you have other questions, would like to schedule a demo, please get in touch with us. We're always happy to have you as our customers and to support you with all the relevant questions with our answers. Last thing I wanted to start, we would like to start a second poll. So what topics of hardness testing would you like us to cover next? I hope we're gonna meet in a few weeks for another webinar. It's gonna be a new year, and we would like to know your opinion. What would be interesting for you? What you're struggling, and this will let us to prepare the best content material and training material for you.
All right. Fantastic. Thank you, Darius.
You're
Um,
very much welcome. Is there anything we shall cover, Tom?
so we do have one question.
Mm-hmm.
Um, with boiler or superheater tubes, 2 to 3 inches in diameter, which are pretty thin, less than a quarter inch in wall thickness.
Mm.
Which method between UCI or Equotip Portable Rockwell would be preferred? And what grip pep would you recommend for that test method?
So
So,
you want to take it?
yeah, so in this case, the best results would be gotten or would be obtained from the Equitip UCI. Even though we do have support feet adapters for measuring on cylindrical objects with the Equitip Portable Rockwell, that is a less preferred method because of the size of the probe support. Generally, the restricted nature that you get in with the boiler and superheater tube walls. So the UCI probe is going to offer you a much better accessibility and because of that reliability, repeatability, we would suggest using a 5 or a 10 kilogram uh, test force to get you an adequate depth of penetration on your indentation. And then along with that, um, what I always tell people is the better your surface preparation, the more accurate your test results will be. So as a minimum, we would suggest using a at least 200 grit sandpaper. In all cases, you should avoid using a grinding stone because grinding stones tend to build up heat and they clog, and building up heat is going to change the hardness and nature of the surface that you're testing.
Exactly. You're actually hardening it without really knowing it. What about flopper disk, Tom? Do you have an experience? I recommend personally flopper disks.
I'm sorry? Flapper
How
discs. Oh,
about
yes, of
how
course.
about flopper disks?
Yes. Yes. So with the lovely portable technology and battery powered angle grinders, a nice flapper disc with the sandpaper flapper discs works very, very well because they tend to not only they'll remove the material for the surface preparation, but they actually self-cool because of the individual pieces of sandpaper rotating around. And we do have some other questions. Any
Yes.
further comments on that, Darius?
I just wanted to say that I have personally conducted several demonstrations, including surface preparation with flopper disks. And there, for example, what we've been doing, we've been combining two methods, but in this case, we're not talking about a small diameter object. Well, it is very similar. It's a round object, but we talk about pressurized vessel or actually vessel. So there we were actually very successful with LEAP and UCI. So flopper disk is definitely something I would recommend from my experience, if it can be used, because sometimes some manufacturing facilities they do not allow that for some reasons. But nevertheless, this is one of the things. And second thing I wanted to highlight is if the user wants to work with a specific standard, the surface roughness preparation between the German standard and ASTM is simply different. So if one needs to somehow specify that according to what standard the surface has been prepared, I would highlight that to have a look at that.
Yeah.
Um, Maybe let me read down the second one on another one. When
Yeah,
verifying the
so
hard
this one,
tester,
the second one, yeah, the second one ties into
please
the
go ahead.
first. How do I know that the roughness is sufficient? So conveniently, we have two ways to do it. That's always a question. Nobody carries a surface roughness profilometer with them in the field. They're rather expensive and fragile pieces of equipment. So we now have to get down to practical ways to tell whether your surface preparation is adequate. The first way to do it is prior to doing any testing, with the Equotip 550, um, we came up with a surface roughness comparator plate. So that's a little plate that fits in your pocket that has the various minimum surface roughnesses
Hmm.
on the surface. So now you have a little piece of hardware where the user that's out there that has to do the preparation can very easily place this comparative plate. Oh, there it is. Thank you, Darius.
Actually, I have a separate slide for this one, just in case someone asks. Yeah.
So you can see there for each different probe, in the case of UCI, the different test forces, we have the different roughnesses, and that gives the user a nice, easy comparison right there on the job site. Um, and you'll note that on this we have UCI of 10N, 50N, 100N. For those of you, the newtons is the correct scientific notation for a force, and a newton is simply 9.8 times the kilogram weight. So 10 Newton is a 1 kilogram, 50 Newtons a 5, and 100 is your 10. The second way that you can tell whether your surface roughness is sufficient is actually indicated after you've tested. So you're averaging a number of readings to obtain a measurement. If you take the recommended 5 measurements, now you can generate a statistical significance on that data. And if you have a very high range, that's an indication that your surface preparation might be inadequate. A high range indicates one of two things. It's either a non-homogeneous material or
Correct.
inadequate surface preparation. So, provided you've already established that you have a homogeneous material or homogeneous specimen under test, then that high range is from your inadequate surface preparation.
Thank you.
Yeah.
A
So we
cool
have
answer, my friend.
yeah, we have more questions, Darius, if you don't have anything to add.
No,
Uh,
that's exactly what I wanted to add, that in homogeneity can be a second possibility in this case. I came across some materials where actually the surface was badly prepared, but also the materials were greatly inhomogeneous, especially when we discuss titanium tubes. Uh, Titanium is probably one of the most challenging materials to convert and to work with because of piling and sinking effect somehow at the same time. But nevertheless, a good statistics would be necessary. I just can repeat what you just said. Nothing to add, Tom.
okay. So let's see, we have some time left. So um, we have additional questions on applications.
Right.
So can it be used for structural steel members like I-beam channels, angle sections? These are sections with thicknesses from 3 millimeters to 15 millimeters. So the standards differ on this, right? ASTM allows down to 5 millimeters, and then below that, if you take into account and confirm that you get accurate results, the DIN standard is stopping at 15 millimeters, I believe. Um, Darius, would you like to comment on this?
Since 2023, the German standard decreased the requirements down to 2 millimeters. So that's the very first thing I could add. So one could apply actually work within the DIN standard, then ISTM standard. Let's say it would be out of the ISTM standard because it provides files millimeters. That's the very first thing. Um, how to decide of the weight of the sample for structural steel members like building columns, beer, or truss members. For we discuss right now probably UCI, and then in fact the criteria is much lower than in case of LEAP. Um, I would say depending on the object, it should be fine. Tom, what's your opinion on that?
Yeah, I think it is fine. So you have thickness, and then you also have structural rigidity that come into play. So there can't be a really hard and fast rule. And if you're talking about the weight of the sample for structural steel, um, even a small sample of structural steel is probably going to be sufficient mass, right? Um, does the temperature of the sample affect the results? This is a multi-part question.
Yeah,
We've done studies, so the short answer is yes, temperature does affect it. However, in the case of lead, which we have done a study on, there is no real significant effect until you get into 400 degrees Fahrenheit or so.
which would be
Um,
how much Celsius? Sorry, Tom. We have also audience from Europe. Not
yes,
everyone
yes,
can.
yes. I'll let you do the Celsius, Darius.
I need to check, to be honest. But one important thing is that at certain point
That's
you cannot 400 Fahrenheit to Celsius. While
that's 205 degrees Celsius,
that is pretty
approximately.
much for the impact body, to be honest, already. For the support ring, definitely. So
Yeah.
it's a little bit hot. And when it comes to UCI, because the method is not specified, but I assume that the question would be about UCI too. Let's not forget, at the end we have a diamond, and diamond is a perfect heat conductor, 3 to 4 times better than the copper. So there is a huge risk of damaging actually the material. So we should not test host surfaces. And secondly, a general comment with increasing temperature, the Young's modulus also decreases. So there is a small impact on that, and this really depends on the magnitude and the temperature, obviously. So that would be also my comment.
Okay. Super. Thank you. So we're running out of time, but I will answer one more question. If we don't answer your question, we will try to get back to you um, offline outside of the webinar here. But this is a question that I would like to answer because I quite frequently see things like this being done in industry, and that is improper notation of the hardness values being reported. So the question actually reads, is a hardness measurement of HLCD the same as HLD? Sometimes I get sent a HLCD from an inspector. So my answer to that would be I don't know because I don't know what scale would be HLCD. That's an improper notation for a hardness scale. So when you look at LEAB test results, they're always reported in HL, and then the last letter is the letter designation of the probe. So HLD represents hardness lead D. If you have a different impact device like the S, then that would be reported as an HLS value. So it's very, very important to use the proper reporting notations, especially whenever you're looking at converting from Brunel values because frequently people are reporting Brunel values, even though the standard says you should be reporting HBW for hardness Brunel with a tungsten carbide indenter. Um, they're saying BHN, HB, whatever. The other error that we see is especially when you're testing in light metals like aluminum, where the default 10-3000 Bernal force is not used. Typically in aluminum, they're using a 10 millimeter ball with either a 1000 or a 500 kilogram test force. And when you change that test force, even though the ball diameter is the same, you're changing that hardness scale that's being reported. So you see differences in the conversion values. So when you look at our default conversions for Bernal in the steel range, they're based off of a 10-3000 indentation. On the aluminum conversion, we're based off of a 10-1000. So those are things to keep in mind. And um, yeah, if you get the HLCD, then we should be asking the reporter exactly what instrument they used and gently correcting them in their reporting notation. That's my opinion, my advice. Darius.
Correct. Thanks for highlighting this. I want to add one thing. This users sometimes use also ISO standard for the conversion, and you exactly nailed the point, Tom. Because, for example, ISO standard, ASTM standard for aluminum specifically, they use two different test forces, and do those results do not match because of the reason why what you have described. I know that we are running out of time. I would like to very shortly answer at least one question. If I have nickel with a M modulus of 2007, do I need a correction? Short answer, and that's why I want to answer it, is no. It's so close to the reference value of 210, then no. Unless user is really equipped and wants to apply this fine correction on himself, but actually no. And then one more thing for a range 2 to 300 vickers and assuming good homogeneity, what plus minus spread of results are considered typical? Well, first of all, it's a very broad question, so let me just nail it straight to the point. It depends on the method, so there are different tolerances based on the method. We assume the good material homogeneity. So the good practice would be staying within what the method allows. For example, for UCI with this range, it would again depend on the test load. If we're using HV5, it would be 4%. And again, depending on the standard. So there are very sub-variants of those things. Let's not forget that the benchtop would be typically 3% within that range, depending on the standard too. So with UCI method, one is not far away. And now, if we discuss, for example, 2% of 200, or 3%, it would be plus minus 6 Vickers. For the UCI, it would be slightly higher, so it's 4% on the laboratory scale, and by the user even 5%. So even 5% within that range is tolerable. Well, once more, it really depends on further details of that question. But we would be very happy if you have that question. Please forward it to us. We'll be very happy to answer that if possible.
Okay. Oh, and then there was a correction to the previous question. The reporting was actually HLDC, so
You
that would
see.
be hardness lead with the DC impact device. It's still yeah, the DC impact device is a lead D device with the loading tube removed. It makes it shorter so you can insert it into restricted areas like boreholes and so forth. So the DC device is still doing a lead D test. So technically, HLDC could be seen as an incorrect notation, but it's not a bad thing because it does tell you that it was done with a DC device. So I don't see a problem there.
All
So with
right.
that, I think we should probably wrap things up and get back
All
with the
right.
folks that we need to follow up with.
All right. I have one slide to comment on after the Q&A session. So I wanted to highlight that this year is a very special for us. We mark our 50 years anniversary. This is where the lead method was born in Switzerland, in Schwarzenbach. This is where Equotip has started. For our old customers, but also for the new ones, we have prepared plenty of opportunities. This is actually by far the largest promotional campaign we've did. So if you are interested in getting, for example, Equotip 550, only this year you'll have an extended warranty, but also plenty of other opportunities like test block bundles for peace of mind. Or if you have essential version of Equotip 550, which is 540, you can very easily upgrade it this year. So once more, this runs only 60 for another 60 days until the end of the year. And I would like personally thank to everyone for joining today. Thank you for asking good questions. Thank you, Tom. And maybe you want to, Tom, you want to add something on top of you, on top of on top of that. Excuse me, it's been a long
Yeah,
day.
no, thank you, Darius, and thank you everybody for attending. And by all means, we have a few days left to take care of the 60 days left in the year to take advantage of these offers for the 50-year anniversary. And yeah, that's all. Thanks again.
Thank you very much.